Hey everyone, welcome to Mr. Winter's AP Chemistry videos. I'm Mr. Winter. Today we're going to be talking about empirical and molecular formulas. Today you're going to need a calculator and a periodic table along with a pen and pencil and some notes. Don't forget that your graphic organizers are linked below. So let's go ahead and get started. Today, we're going to look at first the law of definite proportions and kind of show you why it's important to understand about the empirical and molecular formula. Remember that the law of definite proportions says that the ratio of the masses of the constituent elements in any pure sample of that compound is always the same. What this means is that if we're looking at a pure substance, the percentage of the elements in that compound should be the constant. Now, there's actually some small, tiny issues that come up with this law. And that's going to be compounds that contain elements in the same ratio. Let's look at NO2 and N2O4. For both of these compounds, the percent composition of nitrogen is going to be roughly 30.5%. And the percent composition for oxygen would be 100 minus that. So that would be what, 69.5%. So as far as this goes, you cannot use the percent compositions of the elements to identify a difference between NO2 and N2O4, both of these compounds, which do absolutely exist. So the way we go ahead and do this is with information regarding the empirical and molecular formula. The molecular formula specifically is going to be the true formula of the molecule indicating the number and type of elements. So the molecular formula for nitrogen dioxide would be NO2, and the molecular formula for dinitrogen tetraoxide or tetroxide would be N2O4. These two things are the molecular formula for both of these compounds. As far as the empirical formula goes, this is going to be referring to the lowest whole number ratio of elements within the molecule or compound. So let's go ahead and check this out. Let's look at the molecular formula for three different compounds here and determine what the empirical formula is based off of the information that we have. So first we have C6H6. Now, if you guys paying attention here, the lowest ratio that we can have between the carbons and hydrogens is actually a 1-to-1 ratio. And the relationship between CH and C6H6 is going to be by a multiplication of 6, excuse me. P2O10, P2O10, the lowest whole number ratio in which you can relate the phosphorus and oxygen is going to be P05, and the relationship is going to be a whole number of 2. And the molecular formula for nitrogen trichloride, NCl3, actually already is in its empirical formula state, NCl3. And so the whole number relationship is going to be 1. When we're looking at these things, the empirical formula is sometimes the only way that we scientists can determine the ratio of elements within a molecule. But other than that, this kind of column here is somewhat useless to us, uh, other than if we were to actually have some sort of relationship or way to compare the empirical molecular formula. And guess what? We do. We actually have a relationship. And that relationship is specifically this unofficial equation here, okay? So if you notice, there is a whole number. We kind of went over that whole number relationship between the empirical and molecular formula. That's also going to be related to the masses. So let's see here, the molar mass of the molecular formula, so of the larger one, is going to equal the molar mass of the empirical formula times that whole number. So the molar mass, once again, is related to the molar mass of the empirical formula by some sort of whole number. Once again, this is a really good equation for us to have. It's unofficial and isn't on the AP chemistry reference sheet. So with that being said, let's go ahead and practice this out. An organic molecule is experimentally determined to have the empirical formula CH3O. If the molar mass of the molecule is 62.08 grams per mole, then what is the molecular formula of the organic compound? So generally speaking, when we're reading through these problems here, whenever they provide the molar mass of a substance, that is often going to be the molar mass of the molecular formula. The molar mass of the molecular formula. Because if they provide us the empirical formula, then we can easily go ahead and figure out the molar mass of that thing. So the molar mass of the empirical formula will equal 12.01. So that's the molar mass of carbon, and there's one of them, plus 3 times 1.01. So molar mass of hydrogen, plus 16.00, which is the molar mass of oxygen. We add up all of the substances here, and that's going to be 31.04 grams per mole. Now, hopefully, if you're mathematically minded, you can already see a relationship between the molar mass of the molecular and empirical formula. But let's go ahead and continue this on using our unofficial equation. So the molar mass of the molecular formula is equal to the molar mass of the empirical formula times some whole number. And our goal right now is to figure out what this whole number is. 62.08 is equal to 31.04 times n. Dividing this over, we find that n is equal to 2. So if we take our empirical formula here, CH3O, and multiply it by 2, all those subscripts are multiplied by 2, we find our new molecular formula to have the formula C2H6O2. There is our formula here. Wonderful. I hope you guys have a wonderful day. If you have any questions, feel free to shoot me an email. Don't forget, the graphic organizers are down below. Bye.